this evening's history of mathematics lecture. Tonight will be a little different, but before we get to tonight's lecture, let me make two announcements. We made an announcement last week, but a lot of you were not able to be here because you were doing some farming, 劳动. I hope you had a good time. I saw the pictures from the activities, and it's a good educational experience. But we made an announcement last week, which was that for the 50-page report that you need to make for our history of math lecture, Professor Yao has given you an option. The option is, instead of the 50 pages of writing about stories of mathematicians' lives and accomplishments, you can choose within a 200 period, the last 200 years, so 20th and 19th centuries, the most impactful or most important, in your opinion, theorems or papers that were published in the last 200 years. Write about the 30 most interesting, impactful, or otherwise you find important. You must not only, here's Yuval, you must not only describe the theorems to show that you understand what they say, but also to explain why you feel it's important. So I think this is an important announcement that we don't want our UCO students to miss either. And while we wait for Professor Perez to get ready, there's a second announcement, which is next Monday there is no class, as you may already know. Next Monday, because of the 五一, there is some shuffling, and so our next meeting after this one will happen on May 10th, which is a Saturday. So it's 12 days from today. Okay, so you will have an enjoyable 五一, and I think we are now ready. This is my favorite topic. History of ergodic theory. If you take my courses, you will learn also the history of ergodic theory, but a more modern version. Professor Yuval Perez will give you maybe a broader picture of the development of ergodic theory. So please welcome Professor Yuval Perez.
So, yes, apologies for the late arrival. I kept thinking I have to add one more reference, one more person. But anyway, so I want to thank Andrew Best and Xiangyu Wang for help in preparing this lecture. And one can trace the origins of dynamical systems to the description by Newton of a celestial mechanics using systems of differential equations. But our story really starts with Boltzmann, who invented statistical mechanics, and there is a whole fascinating article about Boltzmann's view of the ergodic hypothesis. Roughly, it says that a mechanical system will reach all possible states within the same energy level and will, over time, visit each set of states with the right frequency. So, Boltzmann was a physicist, not a mathematician. This was made more precise later by Poincare, and then actually, in the right version, proved by von Neumann and Birkhoff, and I'll tell you more about this. You can read about how Boltzmann arrived at this and his discussions with Maxwell in this paper. We'll make the slides available later. So this is a fascinating piece of history. Poincare tried to look at dynamical systems from a broader view, trying to understand what general features many dynamical systems will share, rather than looking at the details of the equations or the mechanics. And one fundamental thing that happens in all dynamical systems that preserve a measure, and basically Liouville measure is preserved in mechanics, so is the phenomenon of recurrence. So that with very minimal hypothesis, so if you have a system that preserves a finite measure, then almost every point, if you examine its orbit, it will return closer and closer to the starting point. So that's one formulation of Poincare recurrence. And when Poincare described that, he understood what was going on, but measure theory had not yet been created. That was the thesis of Lebesgue, 1905. So he talked in a kind of heuristic language of probability, but he understood what was going on. And in particular, this beautiful statement, Poincare recurrence, that almost all orbits return arbitrarily close to the starting point. So he understood that it's not true for all orbits, but almost all orbits. So the kind of general setting that we'll discuss is that of dynamical systems where, so if we want to go from the setting of differential equations to the abstract setting, we can think of, you have some initial conditions, you write the system of differential equations, and you ask how will the trajectory, the path defined by these differential equations look one time unit ahead. So that's if we want to look at discrete time. We can think of time units, we can think of them as very small, where we move 1 unit of time at every step. Of course, we could also parameterize time by the reals and get flows, but I will emphasize the discrete time point of view here. So we can already see the germs of later extensions by thinking of composition operation as a group action or a semi-group action of the positive integers. And so in modern ergodic theory, one studies many semi-groups and group actions. The history was mostly when the group acting was the integers or the reals. So, dynamical systems is a huge subject, and even the topic I will discuss today is very large. So, but it's just part of dynamical systems. So dynamical systems, it depends what properties you want to think of are fundamental to your phase space. Is it a metric space? Is it a manifold? Is your transformation continuous? Is it smooth? The basic setting of ergodic theory takes rather minimal smoothness hypothesis. So we have a probability space, and we can also talk of infinite measures. I won't, but I'll talk about probability space, and a transformation that preserves the measure. So what does that really mean? So if I have any measurable set A, I look at the pre-image, T inverse of A, that should have the same measure as A. So if T is invertible, I could talk about the image of A having the same measure, but without assuming invertibility, the right hypothesis is T inverse of A. So all the points that in one step will move into A, those points should have the same measure as A. That's what measure preserving means, and that's the basic setting of ergodic theory. And there's topological dynamics, smooth dynamics, complex dynamics, arithmetic dynamics, many interesting other topics, and there are close links between them, and tools from one are used in the other. So, Poincare refined Boltzmann's ergodic hypothesis, and first, instead of saying that the mechanical system will reach everywhere, he described it as having the mechanical system will be ergodic, so any set of positive measure will be visited by almost all orbits. So if you have any set, no matter how small, but not completely negligible, so some positive probability, and you take an orbit. Then as you run this orbit, it will eventually visit this set for almost all starting points. So there could be measure zero of exceptions, and these points could be very interesting, periodic orbits and so on, but for almost all orbits, they will visit the set. And so that's ergodicity for Poincare. In the modern language, we like to formulate ergodicity as saying we cannot break up the system into two subsystems, both of which are invariant. So, if your system can be broken into a set A and a set A complement, and T moves A into A and A complement into A complement, then why are you examining them together? You should work on each one separately. So, and life can be more complicated. So actually, if you want to get to an ergodic system, you may have to decompose into a continuum of subsystems in general. But still, there is a general ergodic decomposition theorem that tells you that you can, to understand general measure-preserving systems, it suffices to understand ergodic systems. Now, that's kind of a property of the systems of mechanics. And again, when you say it visits, the system is ergodic, you already Boltzman said, well, you have to fix the energy because you're not going to move from one energy level to the other in a closed system. But once you have, that's kind of an axiom describing your system. And then there is a mathematical conjecture, which is that for every set A, this is measurable sets in our language, for every measurable set, the frequency of visits to A should tend to the relative measure of A as time goes to infinity, again, but not for all starting points, just for almost all. So that's kind of the full ergodic hypothesis as reformulated by Poincare in 1894. And again, I'm not using exactly the language he used. And I'm going to skip ahead to the first proof of that hypothesis, which was a weaker form of convergence, so convergence in L2. And this was achieved by von Neumann in 1931, published in 1932. So of course, you've probably seen the name von Neumann. He invented game theory, big part of operator theory, the first computer after Turing, many, mathematical formulation of quantum theory, so many important contributions. And one of them in this 1931-32 was a proof of an ergodic theorem, what we now call von Neumann's mean ergodic theorem. So it's mean because it's in an LP space. It's not a pointwise statement. So you look at a function f, and to relate to what we did talked before, think of the function f being just the indicator for a set. So 1 on a set A and 0 as a complement. Those are very important functions, f. So then if you look at the average of f along the first endpoints of the orbit of x, so if f is the indicator of A, this is just the fraction of times among the first n that we are staying in A. And then this fraction should tend to, well, what does it tend to? So this is a very general setting. It will tend to the projection of f onto the fixed point of the operator t. So this looks a bit abstract. So let's look, what does this projection mean in the ergodic case? So in the ergodic case, there are no invariant sets, and this means that, except the whole space and the empty set, up to measure 0. And this means that every invariant function has to be constant almost everywhere. So in the ergodic case, which is the most important case, the space of invariant functions is just the constants. And projecting on that space is just integrating. So pkf in the ergodic case is just the integral of f. So then this is, you see, saying that the time average of f along the orbit converges to the integral of f. Pk of f will be the integral in the ergodic case. In general, it's an orthogonal projection on a subspace. Now, Why is not this a really fully satisfactory proof of the Ergodic theory? Because of the mode of convergence. So this is convergence in L2. We have one function on the left, another function, maybe a constant on the right, and we're saying they're getting close in L2. So the difference, if you square it and integrate, goes to 0. That's nice, and it also tells you that along some subsequence, you'll get convergence almost everywhere, but really what was wanted was everywhere, almost everywhere convergence, not everywhere, but at almost every point convergence along the full sequence without having to take a subsequence. And this was proved subsequently by Birkhoff, but there's kind of a story about that. So when von Neumann, so Birkhoff was interested in this problem for many years. For von Neumann, this was kind of a side interest, but he was the first one to get there. So what was unusual at the time for a European mathematician, he submitted his result to an American journal, actually American Journal of Math, where the editor was Birkhoff, because he knew that Birkhoff, is interested in this and would appreciate the result. What Birkhoff actually did is this spurred him to work harder to prove the stronger theorem. So he sat on von Neumann's paper for half a year and only published it together with his paper with the stronger result that made von Neumann's result less impressive. And he actually published them in reverse order. So he was a tough guy. Anyway, this is von Neumann's theorem. And before going on to the fancier Birkhoff theorem, so von Neumann proved this using spectral theory. So it was not such an easy proof. But subsequently, Weiss and also Kakutani found easier proofs that really are almost at the level of a linear algebra course. So a basic fact that you can prove in linear algebra is that if you have a unitary operator, and so you see T, because it's measure preserving, if I think of it as acting on functions in L2, or think of vectors in L2, so then it's a unitary operator. It preserves the norm. And for for general operators, there's some decomposition of the domain in orthogonal decomposition into the kernel and the image of the transpose. But for unitary operators, there's a simpler formulation that the original domain, and this is true even in infinite dimensions, the L2, which is where we think of T as acting now, the space of square integrable functions, can be decomposed in two pieces. One is the invariant functions. K, remember, is the space of invariant functions. And the other is the image of I minus T. So this is all functions of the form H minus H composed with T, but we have to close that space. So the kernel is always closed. The image in this infinite dimensional setting, the image is not closed. So you have to close this. And the direct sum of these two just equals L2. And I'm not going to put the proof here, but the proof is just a few lines. You just show that if a function is orthogonal to all functions in that image, then it must be in the kernel, and it's just a few lines. I'm teaching an ergodic theory class now, so this is one of the first things we do in the class. So this is really not hard to verify, this decomposition. And what Weiss pointed out, once you know this, the ergodic theorem of von Neumann kind of falls out, because you take any function in L2 and you write it as a sum of these two terms. One is in the kernel, so one is a fixed point of T, and the other is in the closure of the image. So in other words, we can approximate F by a function of the form G plus H minus H composed with T. Now, G is a fixed point, so it does, all this ergodic averaging, it's not going to change it. When we take G and compose with T, we just get G. So what we really want, so G is just the projection of F on the fixed points. So what we want to check is that the second part will go to 0. And then there's an easy argument that if we, there's an easy continuity argument that once we show this for functions in the image, then the closure is not going to hurt us. Everything here is a nice bounded, uniformly bounded operator, all these averages. So it's enough really to look at functions of the form g plus h minus h composed with t. So it's enough to look at functions of the second type, h minus h composed with t. And for them, we want to show that the ergodic averages go to 0. And that's easy because we get a telescoping sum. So when we take these and we compose with powers of t, right? So like composing once, you get h composed with t minus h composed with t squared. So everything here, I see. So this f here, I'm sorry, should really be h on the right. So the g doesn't matter, but really think of h being on the right. So when you do this averaging, you will get h minus h composed with t to the n. You divide by n, and this will go to 0. So replace that f by an h. Okay, now Birkhoff's theorem, is technically harder. Now we don't consider it a hard theorem. There are easy proofs, but most things become easier over time. So von Neumann's theorem became very easy, and Birkhoff, well, there are short proofs, but each one involves some trick. So Birkhoff showed that these averages exist. Actually, he showed it for bounded function, and it was Kingman who pointed out that his argument works for all f and L1. But so if you visit Russia, you'll hear there it's called the Birkhoff-Kingman theorem. But Kingman himself said, well, he could derive it just using Birkhoff's ideas, and then so this limit exists for almost all points, and in the ergodic case, this limit is just the integral of f. So taking f, which is the indicator of a, really gives the full justification of the ergodic hypothesis in the ergodic case. So this theorem, became famous, but for instance, about the same time, Kolmogorov was proving the strong law of large numbers for independent identically distributed variables using a very clever truncation argument. And it took a while before Kingman noticed, well, actually, the ergodic theorem is more general than the strong law of large numbers, because if you have a sequence of independent identically distributed variables, you can view it as a dynamical system under the shift. And if you take that point of view, then the strong law of large numbers, which itself is a non-trivial theorem, becomes a special case of the Birkhoff ergodic theorem. Now, one thing that emerged already from starting with Hardy and Littlewood in 1900 is when you want to prove, or in the early 1900s, when you want to prove a pointwise theorem almost everywhere, a very powerful tool, which now we know is an essential tool, is to prove maximal inequalities. So we want to control not one function, but the maximum of a sequence of functions. And this historically happened first in analysis with Hardy and Littlewood, then in ergodic theory with Wiener, Kakutani Yoshida, then in probability with Dubh. So I'll focus here on the ergodic version. And this is a theorem of Wiener simplified and extended by Kakutani and Yoshida in the late 30s, early 40s. And so look at AN. So AN is the ergodic average. This is what we want to show converges almost everywhere. Now, and this is the statement that the measure of the points x, where the supremum of all these averages is bigger than some positive number m, is less than the L1 norm of f divided by m. Now, for this statement, you can and should think of f being a positive function. You can always just pass to the absolute value of f. So think of f being a positive function. Then, you see, if I remove the supremum, I just take one average an, then this average an, it has the same L1 norm as f. Again, think of f being a positive function. Then this average has the same integral as f. So then the statement, if I'm just considering a single an, then the statement is trivial. We sometimes call it Markov's inequality, right? The measure of the points where a function exceeds some level is bounded by its integral divided by the level. It's just a trivial thing coming from definition. So what is non-trivial here is that you have the soup inside there. So you control all these functions simultaneously. And that's the feature of maximal inequality. So as you study analysis, you'll see often maximal inequalities, you have a statement which is trivial without the max. And the best maximal inequalities don't make the right-hand side worse when you throw in the max on the left, and the right-hand side just stays the same. And this is this Wiener maximal inequality, again, extended by Kakutani and Yoshida. And they have a more general version, which I won't go into. But this is really the tool you need here, because what this tells you is that the set of functions where the Birkhoff ergodic theorem holds is going to be closed in L1. Because, so that's what you can easily get from this maximal inequality. If you know the ergodic theorem for some dense set of functions, then the small error you can control using this maximal inequality. And then once you know that, there are many paths to finish off the proof of the ergodic theorem. And my favorite, not the shortest one, my favorite, which I learned from Billingsley's book, is to actually go back. I'm going in the wrong direction here. If we go back to this Rees proof of the mean ergodic theorem, you see, if you have functions of this type, g plus h minus h composed with t, these functions, they're without closure. These functions are dense in L2, hence they're dense in L1. And for these functions, especially if you can take g and h to be even bounded. So take g and h to be bounded, you get a dense collection of functions. And for these functions, you can easily verify the Birkhoff pointwise ergodic theorem. It's the same kind of, the same telescoping sum works for you to prove a pointwise limit. If g and h are bounded, then you have this function. And then these functions are dense by the Rees argument. And then you just need this fact to control the error in the approximation. So this tells you that the error in the approximation is not going to cause you trouble. So when I was, maybe I told you this story before, but I like to repeat it. When I was a postdoc at Yale back in 91, so I'm there on the right, I had the privilege of meeting Kakutani and hearing many of his stories. This photo is from a birthday conference for Roy Adler. So Kakutani is here on the left. Next to him is his student, Roy Adler, who was, this was a conference in honor of Roy Adler in 91. Great ergodic theory conference. Many excellent ergodic theorists were there. I won't go through the list, but let's just continue and tell you, another kind of spectacular victory of ergodic theory in a classic topic of number theory, which is continued fractions. And this is one of the local favorites of, for Yitwa and his students and collaborators. So, but I think everyone must love this. So every number has let's look at numbers in 0, 1, so they have a continued fraction representation. And if they're irrational, this continued fraction representation is infinite. And since we're going to look at typical x, according to Lebesgue measure, typical x are irrational. So we have these AI. And Gauss, long before measure theory, ergodic theory, or anything, he looked at continued fractions. He had very deep understanding of continued fractions. In particular, he pointed out that if you want to shift the continued fraction, so, we write this continued fraction in the form on the right, A1, A2, A3, that just means that's a shorthand because this is not fun to write many times. This notation is shorthand for this continued fraction, and you have to understand this continued fraction really as a limit. So you go up to n, you get some rational number, and you take a limit as n tends to infinity. So if you look at this sequence, and you just shift it by 1, right? So ergodic theorists love to shift the sequence. So we take A1, A2, A3, and we shift it to the sequence A2, A3, and so on. This shift, well, if we want to look at this shift on a point x, what does it mean? It's exactly just taking x, taking 1 over x. So this will get us, just remove this 1 over, and then taking mod 1, which means removing the integer part, staying with the fractional part. That's shifting. Okay, that's, we don't need Gauss for that. But what Gauss observed is that if you formulate this map this way, there is an invariant density. So there is an invariant measure and this measure has a density with respect to Lebesgue, and the density has a very simple formula. It's 1 over 1 plus x log 2. So long before any ergodic theory, Gauss realized the importance of this, and much later, Kuzmin, using ergodic theory, pointed out that once you have this density and you know that it's ergodic under this transformation, which is not hard, then you can find for almost every x what's the asymptotic frequency of every digit. So if you want to know, what's the asymptotic, you take x, which is typical according to Lebesgue measure, and it's the same as x, which is typical according to this measure, they're equivalent, and you want to see what's the asymptotic frequency of the digit 7 in that x. For almost every x, it's the same asymptotic frequency, and you just get it by integrating this density over the interval, from 0.7 to 0.8. So that's, I'm not saying this right. So it's over not from 0.7 to 0.8, over the interval corresponding to A1 equals 7. So it's not 0.7 to 0.8. I've shifted to decimal. So you have to, what? Yeah.
1/7 to 1/8.
1/7. Thank you, Itwa. Yes. So you just, and this is just some simple logarithm, and that gives you the asymptotic frequency of the digit 7. And okay, this is the graph of the Gauss map, but there was more progress. So later, Kingman, with an improvement from Paul Levy in 1935, 1936, used this to get something possibly even more interesting, which is if you take x, which is a continued fraction, and you just truncate, so you stop at the first n, so you get the ratio Pn over Qn. So this is known as the convergent of the continued fraction, and it's also the best approximations. If you want the best approximation up to a certain denominator, they're given by just truncating this continued fraction. So these numbers are important features of x. Even if you don't care about continued fractions, you should care about what are the best rational approximations to an irrational number. And these Pn over Qn give you that. And then it turns out that with a little bit of juggling with the Birkhoff ergodic theorem, and this is even explained, explained in many textbooks, you can get that what is the asymptotics of Qn. So you can think of Qn to the nth root of Qn, or here I've taken a log, and this log converges to just a simple integral with respect to this Gauss density, which so Kingman pointed out the convergence, and Levy pointed out what the value is, and the value is just pi squared over 12 log 2. So very nice answer. And this holds almost every x with respect to the Gauss measure, but hence for almost every x with respect to the Lebesgue measure. Now, an important theme in ergodic theory from the 1930s to this day is to understand which dynamical systems are isomorphic to each other. So, for instance, if I look at this map 2x mod 1, and you have the graph of this mapping here, it's one of the most fundamental maps, and it appears in various guises. So one guise is you take the unit circle, so there the variable, we usually call it z, and you look at z goes to z squared. That's just the same thing using the exponential map going from the interval, e to the 2 pi ix, going from the unit interval to the circle. But here's another important equivalence, that if you have a number x in the unit interval, we know you can write it in binary. And for almost all numbers, this expansion is unique, so we don't care here about the binary rationals that have two representations. So you write it in binary, and you map it to the sequence B1, B2, B3. What is the sequence? If X has Lebesgue measure, then B1, B2, B3 are just independent, identically distributed fair bits. What you would get from tossing an infinite sequence of coin tosses, infinite sequence of coins, all of them independent and all of them fair coins. Half heads, half tails, or half zeros, half ones. So we can map X to this sequence, and if we take X and apply the doubling map here, 2X, it just corresponds to shifting this sequence one step to the left. So this gives you a very obvious isomorphism between two systems. One is this doubling map on the unit interval, the other is the shift map on sequences of bits. Okay, so of course von Neumann was aware of that. He also was aware that some systems are not isomorphic. And here on the left you have this doubling map. On the right you have the map. I didn't draw its graph. Here I chose, we chose to draw its orbits. So you look at the orbit of the map x plus alpha. So this is the map x plus alpha mod 1. You can also draw the graph. And this is just the orbit of 0 under this map, where alpha is some irrational, and we already mapped it to the circle. Now this mapping is actually an eigenfunction. So if you look at e to the 2 pi ix, and you apply the transformation, it's just going to multiply it by e to the 2 pi I alpha. So this transformation has a very nice non-constant eigenfunction. But on the left, von Neumann knew, and it's actually easy to prove, there are no eigenfunctions, except, of course, the constants are eigenfunctions with eigenvalue 1. But that's the only eigenvalue 1, which has only eigenfunction which is constant, because the system is ergodic, and that's it. Von Neumann knew that. So he knew these are definitely not isomorphic. But what he didn't know, so he was applying spectral methods, he asked, this system, the 2x mod 1 and the system 3x mod 1, he asked, can you prove that they're not isomorphic? So what does isomorphism mean in this setting of ergodic theory? We want a map from the left side to the right side, which will preserve measure. So here we have Lebesgue measure on both sides, so we wanted to map Lebesgue measure to Lebesgue measure. And we wanted to commute with the operators. So if we first apply the isomorphism left to right, and then apply 3x, it should be the same result as first applying 2x and then applying the mapping. And it should happen both ways. So that's an isomorphism. If we have it just one way, it's called a factor map or homomorphism of ergodic or of measure-preserving systems. So both homomorphisms and isomorphisms are important. How to show this is not isomorphic? This problem was open for a couple of decades, and the idea of the solution came from an unexpected place, from the work of Shannon in information theory. So Shannon was not looking at dynamical systems. He was, at the time he developed information theory, he was an engineer working at Bell Labs, trying to understand, quantify information, and he borrowed some ideas from Boltzman and Gibbs of statistical mechanics, but extended those ideas to define entropy for a general random variable. So if you have a discrete random variable taking several values. The sum on the top is just over values x where this probability is positive. So you sum the probability times the log of the probability, add a minus sign to get a positive quantity, and that's the entropy of a discrete random variable. Information theory is its own large subject, and he proved many beautiful things about relation between codes and information theory. But one definition he made is relevant here, which is the entropy of a stationary process. So a sequence of random variables is called stationary if when you shift it, you get the same distribution. So x1, x2, x3, the triple x1, x2, x3 should have the same distribution as the triple x2, x3, x4, and so on. So stationarity of a stochastic process is just another way to say that the shift map preserves measure. But we don't assume here that the variables x1, x2 are independent. They have some joint distribution, but it's stationary, meaning it's shift invariant. So this is just different terminologies in different fields. So suppose you look at the entropy of x1 to xn. So a fundamental thing that Shannon proved is that the entropy of a pair of variables is always bounded by the sum of their entropies. And this means that this implies that if I look at the function entropy of x1 to xn, when I have a stationary process, this is a subadditive function of n. So if I look at the entropy of a large block, I break it up in two, the entropy of the large block is bounded above by the sum of the two subblocks. And then there is a very famous calculus lemma called Feket's lemma that tells us that for a subadditive sequence of real numbers, if it's bounded, if the ratio an over n is bounded, we'll get the limit. And in general, we have a limit. It might be minus infinity sometimes. But in this setting, since it's positive, the limit is not minus infinity. So if you take 1 over n times the entropy of the first n variables, this limit exists. So Shannon knew that, and he called that the asymptotic entropy of this sequence. And even investigated things like, what is the entropy of English? English is not really a stationary process, but still he used his discoveries relating entropy to coding to try and estimate the entropy of English, among other things. But for our story, the important thing is that he made this definition. And then Kolmogorov, one of the giants of the mathematics of 20th century, realized that this could be used in dynamical systems. So given a dynamical system, so call the state space E here, you can always partition the system. So this partition, you can think of it, it's just a function on the measure space that takes finitely many values. Here in this picture, it takes 6 values, right? So this is where the function takes value 0, here 1, 2, 3, 4, 5. So this partition can be used to go from a dynamical system to a stochastic process. So if I have a dynamical system, I start at some point x, and I map it to tx and t squared x, t cubed x. And if I don't record the exact point I'm in, but just which element of the partition I'm in, I get a discrete process. And if the original map was measure preserving, then I get a stationary, and I start at x according to mu, then I get a stationary process. Okay, so that's fine, but I'm interested in the dynamical system and not in you see, Shannon was interested in the random variable, so we could say he was interested in a particular partition. But Kolmogorov was interested in the dynamical system. The partition was just a tool. So for every partition, you can get different entropies when you map to the Shannon setting, to a process. So now Kolmogorov did what seems like a scary step. He took the soup over all finite partitions and said, well, that soup is now an invariant. If I have an isomorphism to another system, I will get the same supremum. But this is going to be useless if this sup is infinite. So the key thing he realized is that the supremum will, in the interesting cases, be finite. And moreover, if you have a specific partition where taking this partition and mapping it along generates the full sigma algebra, then that partition is enough to compute entropy. The sup over all partitions equals the entropy over one specific partition. So if we go back to this doubling map, and I'm going in the wrong direction here, sorry. Something. Okay. Okay, let's go back to this doubling map. So for the doubling map, the natural partition we want to use is just the partition of the unit interval into 0, half, and half 1. Because if we use that partition, we just get the sequence of coin tosses, and for that it's trivial to compute. The entropy is just log 2. And what Kolmogorov said, because if we take this partition, if we move it along with the map, then 0, half, and we apply the map to it, we get a partition, and refine with the original partition, we get the partition into 4 pieces and 8 pieces and so on. So if we take this partition, apply it along with the map. So what do I mean by that? I can partition, if I start with this partition in 2 sets, I can get the partition into 2 to the n sets by asking for every point x, where is the orbit going to be in the first n steps? So I just record, is it on the left or on the right, in the first n steps of the orbit. And that gives me a partition into 2 to the n pieces. In this case, they're just going to be the binary intervals. And this partition, as n grows, it approximates the unions of sets from this partition can approximate any measurable set. So what Kolmogorov proved, and then his student Sinai gave a nicer proof later, that's enough to compute the entropy. So I defined the entropy as, or Kolmogorov defined the entropy as a supremum, which makes it an invariant automatically, but then showed you can compute it using one generating partition. And in all the interesting examples, he knew generating partitions. There's a much later theorem of Krieger guaranteeing that there always is a generating partition, but this is needed in practical examples because you can usually just see one. Okay, so that's what Kolmogorov did. But then, so he answered for Neumann. He showed that the doubling and the tripling maps can't be isomorphic because one has entropy log 2 and the other has entropy log 3. And so they cannot be isomorphic. But you get more. If there is a homomorphism from a system X to a system Y, then the first one has to have higher entropy. So again, this follows immediately from this definition of sup over partitions. So you cannot increase entropy by a homomorphism. But this naturally raises the question, if I'm interested in coin tosses, or more generally in IID variables, independent identically distributed variables, is entropy the whole story? If two systems have the same entropy, will they be isomorphic? So, Kolmogorov's maybe most famous students, one of his most famous students was Yaakov Sinai, who got the Abel Prize much later, but still when he was a student, he went a long way in this direction and showed that if you have two Bernoulli systems, so it means systems just where the random variables are independent, identically distributed. If one has higher entropy, then there is a homomorphism from X to Y. So you can map X to Y in a way that commutes with the shift. So what if the entropy is equal? Then, of course, Sinai's theorem will tell you that you can go from X to Y by some complicated homomorphism, and there's another complicated homomorphism that you can go from Y to X, but these are not inverses of each other. different homomorphisms. And to really show that the two systems are the same, you want to find an isomorphism. So this is a famous result of Don Ornstein, who later in 1970, early 70s, showed that indeed if two Bernoulli systems have the same entropy, then there is an isomorphism from X to Y. And his proof of this created a large section of modern ergodic theory, sometimes called Ornstein theory, but there are other important contributors. And this, going into detail of this is beyond the scope of this evening, but this was a real breakthrough. And I understood from Professor Yao that he was in Stanford at the time when, or shortly around the time when this was obtained. So here's just a picture of Ornstein, Sinai with two other famous ergodic theorists, Marina Ratner and Jack Feldman, and their achievements are fantastic, but would take a longer time to describe. So I just chose two specific results, not necessarily their biggest ones, but I'll just tell you what they are. So, because this is something that actually Andrew, my co-author here, and I are currently interested in, which is there is a notion of Kakutani equivalence. So two dynamical systems are equivalent if I can find in each of them a set, so that when I look at the dynamics only when it returns to this set, these two restricted dynamics are isomorphic. So it's a looser notion than isomorphism. Instead of saying the whole systems are isomorphic, I can find a piece here and a piece there, so that if I look at the dynamics only when it returns to this piece, these pieces are isomorphic. This is called Kakutani equivalence. We saw Kakutani before, and Jack Feldman characterized the class that there's a large class, surprisingly large, of what we now call loosely Kronecker systems that are Kakutani equivalent to just a rotation on a circle, which is a very specific map. Not many are isomorphic to that. It's Kakutani equivalent to a large class, and but one of the many breakthroughs of Ratner that she showed that the horocycle flow, a very important map in dynamics, again, maybe Yitwa's favorite, this one is loosely Kronecker. So I'm just mentioning this, I can't go into, but this is a great, I love this photo. Next, I want to tell you about another discovery with these partitions, which started with Roy Adler. Remember, we saw another picture before of Roy Adler in his birthday conference, and Benji Weiss, one of my teachers. So in 1967, they were both working at IBM, and they discovered that if you look at 2x2 invertible integer matrices, they are acting on the two torus. And if you look at these, you can find partitions so that these partitions are generating. And when you look at the orbit along this, and you use this partition to map the orbit, you just get a Markov chain. So it's not an IID process, but it's a Markov chain. Markov chains, it's a finite Markov chain, so we understand these very well, finite state Markov chains. And, and they show that the boundaries are just polygons of these Markov partitions in this special case. Shortly thereafter, Sinai showed Markov partitions exist in a much more general setting. But since I mentioned Weiss, I should mention he was just here last November, visiting the Great Wall with his wife. And we hope he will visit again soon. But anyway, a year after the Adler-Weiss discovery, Sinai found that Markov partitions exist in a vastly more general setting. So basically, the key property of automorphisms of the torus, there is one direction of stretching and one direction of contracting. And you can have maps that are not linear, that have where the directions can be partitioned into a stretching and a contracting direction. And if you don't have any kind of rotation part, then these are, these are nice maps which admit Markov partitions. So this is a famous paper of Sinai in 1968, Russian math survey. Yes?
Could you say how this relates to the result of Krieger that you mentioned? Krieger, the result that...
there is a generating partition.
Yes.
So that partition gives you a process, but this process is not going to be a Markov idea. It's going to be one stationary. The point is that if you take this partition and move it along with the map and refine, you get the sigma algebra. That's Krieger's theorem. Has nothing to do with this really, or little to do. This is for the power of Krieger's theorem is that there are basically no hypotheses. It's always true. Here we look at very specific maps, in the case of Adler Weiss, and somewhat specific, but still a wide class, what's called Anosov maps, and more generally axiom A diffeomorphisms. I'm not going to go into those definitions. They all, 1968, a famous paper by Sinai showed the existence of Markov partitions, and this was some recursive construction. It wasn't clear what do they look like. They certainly didn't look, the construction was not as neat as the Adler-Weiss construction, but was much more general. And indeed, later, shortly after, Rufus Bowen showed that for most cases, except these cases looked at by Adler-Weiss, for most cases in higher dimensions, even for automorphisms of a three-dimensional torus, the pieces have to be, if it's not decomposable, there is a Markov partition we know from Sinai, but the pieces have to have fractal boundaries. The boundaries of the pieces in the Markov partition have to have dimension bigger than d-1. So really, really fractal boundaries, a remarkable discovery. I want to move on to one more important theme, and the evening will run out before we cover even the most important themes. But one other important theme, where smooth dynamics connects with ergodic theory, is in calculating Lyapunov exponents. So suppose first I have a map T, just a map of an interval to itself, not a linear map. And I want to understand high iterates of this map. So the key thing is to understand where are the fixed points and where the map is contracting, or the high iterate, where it's contracting, how much it's contracting, how much it's expanding. In other words, we want to understand the derivative of high iterates of the map. So that's a basic thing in smooth dynamics, one-dimensional, higher dimensional dynamics. Well, using the chain rule, we can write this derivative as a product of the derivative of t along the orbit. Okay, and if we want to understand it, so we want to understand it at periodic points, but if we want to understand it for a typical point, then we can just take this log, and we get the log of a product is the sum of the logs, and we can just apply the Birkhoff-Ergodic theorem to get the existence and sometimes to calculate this limit for typical x. So that's great, very useful. But that's one-dimensional. Now what happens if we're in d dimensions? We can start this thing, but the step we can't do is write the log of the product as the product of the logs. So really, in the high-dimensional case, we don't just have a number, we have a matrix, so we have to take some matrix norm, and log of the norm is nothing like the norm of the log, so we can't just do it in high dimensions. We can do the first step and interpret this T prime as matrices, but, but we can't do the second step, which is write the log of the product. If the matrices commute, so we have these matrices, which are the differentials of T along the orbit. If we're lucky, and this is very rare, and these matrices all commute, you can jointly diagonalize them and reduce to the one-dimensional case. But this is a very special situation. Usually you can't do that. And then what do you do? So Furstenberg and Kesten, motivated not just by this, but by other reasons too, proved a theorem that allows you to handle such products. This is, so, theory of random matrices is very popular, but this is a different thing. This is random matrix product. So in theory of random matrices, you take very large matrices and try to understand the spectrum. In the Furstenberg-Kesten theorem, you take fixed matrices of size. They could be 2 by 2 or 5 by 5. You take product of many such matrices, stationary, and you want to understand how fast does this grow. So you take the product of these matrices. So in the application, these would be the derivatives of t along the orbit. So these would be matrices. And we take differentials of the t along the orbit. We take product of these along the orbit. And then we want to understand the growth of this norm. So it will grow exponentially. We take a log, divide by n. I want to understand the asymptotic. And Furstenberg-Kesten proved the limit exists. And a couple years later, Furstenberg wrote an important paper that tells you how you can write this limit as some integral with respect to a somewhat mysterious measure. Still useful, but not very easy to compute with. But a lot of insights in this, both this joint paper and the subsequent paper of Furstenberg called non-commuting matrix products. And in particular, so very important things I won't have time to discuss, but at least the Furstenberg-Kesten theorem, they had to work pretty hard just to show the almost everywhere convergence. And one thing they used, but it wasn't enough for them, was the fact that you can choose whatever matrix norm you want, because that will only change by a constant that will wash out in the limit. But so you always choose a submultiplicative norm, like an operator norm. So norm AB will be less than norm A. So you get some subadditivity when you pass to the log. So oops, there's a mistake there. So this should be, this is norm AB should be less than norm A times norm B. There is a typo on the right there. Sorry about that. So anyway, what Kingman realized in 1973, so 12 years after the Furstenberg-Kesten theorem, again, sorry about the typo. So that should be norm AB less than norm A times norm B. Okay, what Kingman realized is that you can prove an ergodic theorem under very weak hypothesis. Just you have a sequence of functions, and they satisfy this kind of inequality. So the function at time n plus n is bounded by fm plus fn composed with t to the m. So if you're in the setting of Birkhoff, you would just use fn to be the sum of the first n iterates of f, and you would satisfy this inequality as equality. So the case where you have equality here is exactly the same as Birkhoff ergodic theorem. But the case of inequality holds in much more general settings, and in modern probability, this is an absolutely essential tool. We use it all the time when we study percolation theory in statistical physics. It's a very important tool. But one of the motivations and applications was to give a joint extension of the Birkhoff ergodic theorem and the Furstenberg-Kesten theorem. But he was also motivated by other applications in probability. I want to go to, I mentioned Furstenberg once, I'll mention him again. He was my advisor, so so you'll hear a little more of his theorems. But so an important development in combinatorial number theory happened in 1975 when Semeredi proved a conjecture of Erdős and Turan from 1936 that says if you have a set with positive upper density, which means that the frequency of S inside 1 to n, you see the definition here of upper density, you just take S intersect with 1 to n, divide by n, and take a limb sup. That's the upper density. Upper because we're taking a limb sup. So if a set has positive upper density, then it contains arbitrarily long arithmetic progressions. So this was conjectured in 1936, and Erdős was still around when Szemerédi solved this, and there was a $5,000 prize. And when Szemerédi accepted the prize, he said he will accept it, but he's worried this may break the minimum wage laws because he worked on this for 10 years. Anyway, his proof was very sophisticated combinatorial proof that had many, but a couple of years later, Furstenberg realized there's also an ergodic proof, and both of these proofs have been very important in future developments. And if to say kind of a slogan of Furstenberg's proof is to break up a general dynamical system into components, some that look like rotation and some that look independent. And by showing that every system can be, to some extent, be approximated by these combinations. And one interesting thing, he showed the connection of Szemerédi's theorem to a refinement of Poincare recurrence. So Poincare recurrence in particular tells you that almost every point, if you take a set of positive measure, then almost every point in that set will return, the orbit will return to that set, even infinitely many times. But Furstenberg says not only will the orbit return, but for almost every starting point, there will be infinitely times n where the orbit will return along this arithmetic progression. And once you have that, it's actually easy to show this is equivalent to Szemerédi's theorem. So that equivalence is quite soft. But proving Szemerédi's theorem the Szemerédi way or the Furstenberg way, that's not soft. So there's some work involved. But there's a beautiful book by Furstenberg called Recurrence in Ergodic Theory and Combinatorial Number Theory that explains these connections as well as the proof. Here's another theorem proved about the same time by Furstenberg, by different methods by Furstenberg and Sarkozy. Furstenberg using dynamical methods, Sarkozy using analytic number theory, which is if a set has positive density, then you can find a pair of numbers in the set who differs by a square. So this is connected to the way Furstenberg derived it is he showed that Poincare recurrence theorem holds with the return time being a square. So if you want, you are in a set of, for any set A, almost every point in A will return to A. So Poincare tells you they return sometime to A. Furstenberg tells you they will return at some time which is a square. And then he can derive the same theorem, which at the same time Sarkozy derived by different methods. And an extension by Bergelson, who's my mathematical brother, also another student of Furstenberg, and his student Leibman says that you can take polynomials. So as long as these polynomials vanish at the origin, you can find, instead of arithmetic progressions, you can find these points, these polynomial configurations. So, as I told you, ergodic theory is driven not just by actions of one operator, but actions of a group. There are many interesting problems. One of my favorite is another theorem, another problem of Furstenberg that's still open. I want to tell you about that. So if you look at, let's look at the circle, unit circle. So we know that Lebesgue measure is invariant under z goes to z squared. It's also invariant under z goes to z cubed. So in other words, if we go to the unit interval, we have the doubling map and the tripling map. Lebesgue measure is invariant under both. But each of these mappings have many other invariant measures. So the circular rotation is actually uniquely ergodic. Only Lebesgue measure is invariant. But x goes to 2x, you can build many invariant measures. just because you can look at the binary representation and give different distributions to the digits. And similarly, for the tripling map, there are many invariant measures. But besides Lebesgue, are there any invariant measures that are invariant both under 2x and under 3x? The answer is yes. If you look at the fifth roots of unity on the circle and put uniform measure on them, in other words, put uniform measure on the points 1/5, 2/5, 3/5, 4/5, and 0, that uniform measure is invariant under both maps. So Furstenberg conjecture is that the only jointly invariant measures are some special atomic measures and Lebesgue measure. So every non-atomic invariant measure, and every non-atomic invariant measure must be Lebesgue measure. And this conjecture has been important in the ergodic theory. It was proved first under a restrictive hypothesis by Russ Lyons, and then more generally by Dan Rudolph, that this conjecture is true for measures of positive entropy. So if you have a measure which has positive entropy under one map, then it has under the other map, and in that case the conjecture is true. But in general, we don't know. And the zero entropy case is still wide open despite 55 years of attempts. There's a connection to probability, and here I take the liberty of giving you an example of my own paper. So this is the main journal of ergodic theory in dynamical systems. And ergodic theory has played an important role in probability. And I just give an example of my own paper, but there are many papers where ergodic theory is used in probability. And the most useful place is in the theory of random walks in random environments. So you have some random environment. In my case, it was with my two co-authors back in 95, 6. This was, so it says 2008, but this paper is from 95. So, this was when it was uploaded. So you have some random environment. In our case, this environment came from a branching process. Often this environment comes in the lattice. And you have a particle doing a random walk in this environment. You want to understand how fast the particle moves. This is generally very hard and many open questions, but the most powerful technique is called look at the environment from the point of view of the moving particle. So as the particle moves through the environment, it may not see the original environment. It may see a different environment. And asymptotically, it will see some typical environment. And if you can understand that environment, then you can use ergodic theory to understand how fast the particle moves. So understanding invariant measures on the environment that are somehow equivalent to the original is the key to understanding speed. And we did that in the case of trees, but doing it in the case of lattices is an ongoing effort in many settings. I don't have much time, but I want to mention a few of at least a couple of the, key people working in ergodic theory. So one is Elon Lindenstrauss, that we used ergodic theory to make great progress on the Littlewood conjecture in number theory, and I don't have time to discuss the details of that, but that conjecture is still open. But what Lindenstrauss and his co-authors did is show that the set of exceptions has Hausdorff dimension 0, so very, very unlikely exceptions. Many other innovations, and again, I took a liberty of showing one of my joint works with Elon, which is understanding how entropy changes under convolution. So this was work with Elon and another co-author, David Meiri, in 26 years ago. And I won't go much into the details of that. We mentioned one other field medalist who works in ergodic theory and applies methods both from ergodic theory and smooth dynamics to questions coming from physics. This is Arturo Avila, who was just here last year for a visit. I can prove that. And so he uses ergodic theory in a really spectacular way to find formulas for Lyapunov exponents where it wasn't expected to be possible, analyze Schrödinger operators, and CAM theory is Kolmogorov, Arnold, Moser. So again, I don't have time to discuss these. One more who doesn't appear in these slides is Jean Bourgain. So after Furstenberg proved his basic theorems, Furstenberg was interested in the recurrence aspects, but he also proved ergodic theorems along, what he called non-conventional ergodic theorems along the squares. So instead of looking just at the average of f of x, you look at the average of f of x multiplied by f of t to the nx multiplied by f of t to the 2nx. And you take this product and you take the averages, and he showed these converge in L2. So this was part of his proof of his refinement of Poincare recurrence. But whenever you prove something converges in L2, you can ask, well, is it almost everywhere converge? And none of Furstenberg or his students could do that. But Jean Bourgain was visiting Israel at the time, and he took that challenge, and he did prove almost everywhere convergence in that setting. And I still remember I was just a student at the time, and Lior Tzafriri, a functional analyst who was working with Bourgain, came to us with a big smile and said, well, now you also have something in your subject which you don't understand. So anyway, it's getting late, so I'll finish here, and thank you for your attention.